Hello, Year 9. We're back here again, and today we are going to be investigating something called gradient intercept form, and particularly using what's known as the gradient intercept form of a linear equation of a straight line to sketch lines. So in previous lessons, we looked at sketching linear equations, so sketching straight lines on a Cartesian plane like we have here. We've looked at a couple of different methods already. One of them was we got a formula and we worked out the x-intercept, the y-intercept, and we drew a line, right? That was one of the approaches we used to draw a linear equation. That was linked in with exercise 4b. The second approach emphasised that to draw a straight line, all we really needed was 2 points. So if we could get any 2 points from a formula, we could draw a straight line. And that was covered particularly in 4C and was particularly needed when you had lines that went through the origin, when you had lines that went through 0, 0, and you needed to get that second point. Today, we are going to use the gradient intercept form to sketch linear equations. So this is where we are at today. Now, I have already introduced to you the concept of gradient intercept form. So this isn't a huge leap what we're doing today, but it is important and it is about bringing together the logic we've done in recent lessons. So gradient intercept form was this thing, y equals mx plus c. Right, that's gradient intercept form of a linear equation. If you put different x values and you get different y values, and you can do lots of dots and you'll end up with a straight line. Look back over the recent videos if that's a little bit weird. What you need to remember, particularly for today, is m is the gradient and c is the y-intercept. Now, when it comes to graphing, using the gradient and the y-intercept, which is what we're doing, you do this first. You can always put the y-intercept on here first. This is going to be shown by 3 different examples, so don't fret. But we essentially mark the y-intercept on the graph first, and then we use the gradient to find additional points. Now, there's a particular definition of gradient that will do you a lot of favours here, and I do remember showing it to you in a previous video where I was happily walking along across in front of you and saying gradient's always in this direction, gradient can be up, gradient can be down, but we're always going across, we're always going to the right. So that was a bit of theatrics in a previous video. But what you need to remember about gradient to make this all tie together, gradient is the change in y for a change of 1 in x. This is always shown much better via examples, and that's why that's the focus for today. But it is the change in y for a change of 1 in x. Every time you go over 1 in x, the gradient is the up or down you're going. If the gradient's positive, every time you go over 1 in x, it'll be going up some distance. If the gradient's negative, every time you go over 1 in x, it'll be going down. But let's demonstrate that. Let's do this. So I have 3 formulas here that I plan to demonstrate manually doing. And in fact, I'll probably show you in the background here. I'll also put them in the Desmos graphing calculator. Remember www.desmos.com. While you've got technology, that's actually a nice way of checking that you've got what you should, because you can just put formulas like that straight into Desmos and they work. So behind me here, I can actually see exactly what all of these should look like. It's very pretty, but I'm not showing you. So let's do this. First example, y equals 3x take 2. The first thing you might note is, gloriously, this is already in the format of y equals mx plus c. It's already in that format. Y is at the front, something x plus something. Fantastic. Okay, it says subtraction, but you know what I mean. So, first thing I'm going to point out is what's the gradient of this line? Gradient, m, is in front of the x. M, in this case, is 3. What's the y-intercept? The y-intercept's the thing hanging off the edge here. Remember, the negative always belongs to what follows it. So the y-intercept here, c, is equal to -2. From that, I can actually graph this line. So what colour should I do the first line? It was done in red on in my background here, so I might use red for it, so that hopefully we're looking at the same as that in the end. So as I said before in the introduction, the first thing you can put on here is the y-intercept. A y-intercept of -2, you've got a point, right? That's just where the y-intercept is just where it crosses the y-axis. And now for the gradient. The gradient says for every change of 1 in x, as we're going up in x, always going to the right, always to the right. Every time I go across 1 in x, it's telling me that I should be going up by 3, right? It's the change in y for the change of 1 in x. So every time I go across 1 in x, it's going up by 3. So if I go up another one, so it's gone up 3 there. If I go across another one, it should go up 3 again. You'll end up with a point up here. I can keep doing that in the pattern if you want, but you get the idea. For every change of 1 in x, it's going to be going up by 3 in this case. So that's going to give me my line. That's my y equals 3x subtract 2. That's it, graphed. To me, that's easier than the other methods, once you get used to it. Let's look at the second line now. All right, the second line is a little bit weird. You may have to notice that -x over 2 is the same as writing -1/2 x. It's the same thing. That's going to give away the gradient a little better. Do you want to tell me what the gradient is? M is equal to -1/2. That's what's in front of the x this time. And what's c? What's the y-intercept? There's nothing there, is there? Which means that the y-intercept is 0, right? So the y-intercept is 0. From that, we have enough to graph this. So on my diagram it's blue, I'm going to use blue for this. So start off with the y-intercept. Again, every time I graph these lines, I'm going to put on the y-intercept, then I'm going to apply the gradient. The y-intercept 0, so it goes through the origin, as do all equations of that form. Remember, anything that's just y equals mx is going to go through the origin. Now, this is interesting though. The gradient is -1/2. So that means that for every change of 1 in x, every time I go over 1 in x, it's going to be going down by 1/2. It's down because it's negative, and it's 1/2 because it says 1/2. So it's going to be going down 1/2 each time we go over 1 in x. And that's going to keep going forever. It's a bit hard to get that completely accurate using a whiteboard, but you get the idea. For each change of 1 in x, it goes down by 1/2. So I'll put my... and do a nice line through the whole thing. And I've got my second line, which is y equals -1/2 x. Right, the third example I'm going to do here has another trick to it. What's the issue with that thing? What's wrong with 3x plus 2y equals 4? It's not in the standard format. To be able to read off the gradient and the y-intercept, you need it in the form of y equals something x plus something, right? It's got 2 y's and it's not in the right format. You need to be able to use if you're confronted with something like this, you need to be able to use your algebra skills to rearrange it first. So we need to rearrange it so it's in the form of y equals mx plus c first. All right, you can do that a number of different ways. But the most obvious to me is, well, look, I've got this 3x out here. That's a bit of a pain. I'm going to get rid of it. Opposite of adding 3x is subtracting 3x. Which will give me 2y equals negative 3x plus 4. Yes, I didn't write 4 subtract 3x. Why did I put the negative 3x in the front there? Because it's closer to that format. Remember, 4 to subtract 3x is the same as negative 3x plus 4. That just makes it so much closer to what we actually want here. So that's why I'm doing it. Now, here I still have 2y. I need it to just be y to be in the standard format. The opposite of multiplying by 2 is dividing by 2. If I divide both sides by 2, I end up with y equals negative 3 halves x plus 4 divided by 2 is 2. Remember, you have to divide everything by 2. Be very careful with your algebra there. Alas, now we at least know what we're dealing with. We have a gradient there. We have a gradient of negative 3 over 2, negative 1.5. So m is negative 3 on 2, and c is just 2 on the edge there. So as I've done with every other example so far, and this one's going to be in green to match back here, first I'm going to do, see, I've got it in y equals mx plus c, I've got the gradient, I've got the y-intercept. I show the y-intercept first. The y-intercept's positive 2, which is up here. And what it's saying is that for every change in 1 in x, it's going to be going down by 1.5. We see that, people? That's 1.5 negative. So we're always walking to the right, always going in that direction. Every change of 1 in x, down by 1.5. So here it'll be down to 0.5. Across another one, drops 1.5. Oh, it's actually going to intersect that line precisely at that point because it's going to be at negative 1. Go across another one. It's got to go down another 1.5. It'll be down here somewhere. All right, every time we go across by 1, it'll be going down by 1.5. Draw a line. That's our third line. That one there is our new friend. I'll use the original equation on it. 3x plus 2y equals 4. There we go, ladies and gentlemen. That is how you use the gradient-intercept form. Read off the gradient, read off the y-intercept, and you can sketch straight lines. And to show that, yes, not completely losing the plot, that's what we had here. And this is what I had on the computer. Pretty cool, huh? All right, go forth and enjoy 4E. Cheers.